Welcome to Mastering Solutions. This diffraction grading problem is a little bit tricky to get through. We need to figure out how many bright spots can be seen with the information that they gave to us. So they tell us that the 500 lines per millimeters is the size of the diffraction grading that we have. So we can use that to solve for D. So D is the width of the grading divided by how many slits there are. And they tell us that in 1 millimeter, there are 500 lines or slits. And so we have 1 times 10 to the negative 3 meters divided by 500 slits will give us the value for D. The 500 nanometer is the wavelength of the laser, so 530 nanometers, which of course is 530 times 10 to the negative 9 meters. And how many spots? So we need to figure out the maximum number of M that we'll see on this. Now for the diffraction grading for the bright spots, you have to remember that we have to have a positive number. So it has to be 1, 2, 3. Obviously the central one's going to be 0. So we know it has to be a positive whole number, but how do we get there, right? And I feel like I think of this maybe differently than a lot of people, but how it makes sense to me is, let's say that here is our diffraction grading right there, and we're shining it straight this way, and then here is our viewing screen over here, right? So here is going to be M equals 0. And then for every M value, as we go over, there's going to be some angle there, right? So here's theta for M equals 1. And then if we go over, that's going to be another theta for M equals 2 and 3 and 4 and whatever, right? But the maximum number, the angle that we can go, we have a hard wall right here, right? We can't go more than 90 degrees. That doesn't make any sense. So the maximum that we can go is 90 degrees for theta. So the equation that we'll be using is sine of the angle is equal to m lambda over d. Now we're trying to solve for m, so let's move d and lambda over. So we'll multiply both sides by d, and we'll divide over lambda, divided by lambda equals m. And so we want the maximum number that we can get here, right? So we'll be using sine of 90 because that's the limit. We can't go past that. So if we do in our calculator sine of 90, that's 1. And so we can basically simplify our equation because sine of 90 is 1. So m is going to be equal to d divided by theta will give us the maximum m that we can get here. So d, we said, is 1 times 10 to the negative 3 meters divided by 500 slits. And then we'll divide that by the wavelength, which we said is 530 nanometers, which is 10 to the negative 9 meters. And so if we go to our calculator, we have 1 times 10 to the negative 3 divided by 500 slits is D, divided by 530 times 10 to the negative 9 nanometers. So 3.77 is the maximum M that we would get. But to see a bright fringe, like we talked about up here, you're only going to see one at a whole number. So the M max that we would see is going to be 3 fringes. Now, what does that mean for the answer? Don't put 3, because what that means is right here, we'll get a central fringe, right? And then on every side, we'll see one M1 and M2 and M3. And over here, same thing, M1, 2, 3. So we're going to see 1, 2, 3, 4, 5, 6, 7 bright spots. Because they say how many bright spots could be seen on a screen, not what is the maximum M. We just use this to conceptually see how many bright spots we'll find. So we will see 7 bright spots for this diffraction grading question.